Welcome back to our ongoing deep dive into the OEIS.
Um,
Today we're diving into sequence A000065.
okay.
It might seem deceptively simple at first.
Uh-huh.
It represents -1 plus the number of partitions of an integer.
Right.
But as we'll discover, this sequence has its fingers in a surprising number of mathematical pies.
What's so fascinating about A000065 is that it acts as a bridge between seemingly disparate areas of mathematics.
Okay.
We'll see how it connects to geometry,
Interesting.
graph theory,
Cool.
and even offers insights into the structure of real-world systems like supply chains.
Supply chains.
Yeah.
That's not what I expected to encounter in a sequence about partitions.
Yeah.
Let's start with something a little closer to home, like the geometry connection.
Okay.
What can you tell us about that?
One of the first places A000065 pops up is in the world of simplices.
Simplices.
These are the simplest possible shapes in any given dimension.
Okay.
Think of a triangle in 2 dimensions.
Right.
A tetrahedron in 3.
Okay.
Our sequence tells us that a of n plus 1 gives you the number of different n-dimensional simplices you can create with sides of integer length and a diameter of n.
Okay, I'm going to need a little more on that.
Sure.
When you say diameter of a simplex, what exactly do you mean?
Imagine you have a tetrahedron,
Uh-huh.
a 3-dimensional simplex.
Right.
The diameter is the longest distance between any 2 points on that tetrahedron.
I see.
So our sequence is essentially counting how many unique tetrahedra you can build with whole number side lengths and a fixed diameter.
So it's not just about how many ways you can break down a number, but also about how those parts can be used to construct these fundamental geometric shapes.
Yeah,
That's pretty neat.
exactly.
And it highlights how this sequence is about more than just counting partitions.
Right.
It's about understanding the structures that can be built from those partitions.
Yeah.
Let's move on to graph theory.
Okay.
I know graphs can be used to represent all sorts of things. I'm curious to see how A000065 fits into that picture.
This is where things start to get really interesting. A000065 also describes the number of graphs with n vertices and a tree width of n2.
Okay.
Now, tree width is a way to measure how tree-like a graph is.
So a low tree width means the graph is very similar to a tree structure.
Precisely.
Good.
A tree width of n2 means our graphs are almost trees, but with a touch more complexity.
Interesting.
So A000065 isn't just counting simple tree structures.
Right.
It's also counting the number of graphs that have this slightly more intricate structure.
It sounds like this sequence is revealing a kind of hidden order in the world of graphs.
That's a great way to put it.
Yeah.
And this idea of hidden order becomes even more apparent when we look at how A000065 relates to supply chains.
Now that's a connection I'm really curious about.
Yeah.
How can a sequence about partitions tell us anything about the complexity of supply chains?
Think of it this way.
Okay.
Any complex system, like a supply chain,
Right.
can be broken down into interconnected subsystems. The way these subsystems are linked together,
Yeah.
what we call their topology. Okay.
Can have a huge impact on things like efficiency and resilience.
Makes sense.
In a 2013 paper, researchers Modrak and Martin used A000065 to create a scale for measuring the complexity of these supply chain topologies.
So the way we partition a number can somehow reflect the way a supply chain is organized. Can you give us a more concrete sense of how that works?
Imagine a simple supply chain with just a few linear steps. That would correspond to a partition with very few parts.
Right.
Now imagine a highly interconnected supply chain with multiple suppliers, manufacturers, and distribution channels.
Okay.
That would correspond to a partition with many parts,
I see.
reflecting the higher level of complexity.
Okay.
What Modrak and Martin did was to use the properties of A000065 to develop a mathematical framework for analyzing these different levels of complexity.
So this seemingly abstract sequence about partitions gives us a tool for understanding and quantifying the complexity of real-world systems.
Exactly.
And what's truly remarkable is that this is just one of many connections that A000065 has to other areas of mathematics. We haven't even touched on its relationship to rooted trees or certain types of differential equations.
We've definitely only scratched the surface here,
Right.
but I think this is a good place to pause for now.
So good.
Listeners, stay with us as we continue our deep dive into the surprising world of A000065 in our next segment.
Okay.
We've seen how A000006 connects to geometry and graphs, and even has implications for understanding supply chain complexity.
Right.
What other mathematical landscapes does this sequence touch upon?
Let's delve into the realm of rooted trees.
Rooted trees.
Structures used extensively in computer science and other fields to represent hierarchical data.
Okay.
Interestingly, A000065 emerges here as well.
You mentioned rooted trees are used for hierarchical data.
Yeah.
Could you give us a quick refresher on what that means exactly?
Imagine a family tree, but instead of people, we have data points.
Right.
The root is at the top, and all other data points branch out downwards.
Okay.
This hierarchical structure is crucial for organizing and searching information efficiently.
So how does our sequence A000065 come into play with these rooted trees?
The connection lies in the specific structure of these trees.
Okay.
A000065, in this context, represents the number of rooted trees you can create with n+1 nodes where the height of the tree is exactly 2.
When you say height of 2, you're referring to the number of levels in the tree, right?
Yes.
Okay.
A height of 2 means we have the root node at the top,
Uh-huh.
one layer of nodes directly below it,
Yeah.
and then the leaves, the final nodes at the bottom.
So A000065 is telling us how many ways we can arrange those nodes within this specific 2-layer tree structure.
Right.
But why is that significant? Why focus on a height of 2?
It might seem like a specific constraint, but trees of height 2 are actually quite fundamental.
Okay.
They represent a basic building block for more complex trees. Understanding how many variations exist at this foundational level helps us understand the potential complexity of larger tree structures.
That makes sense.
Yeah.
By studying the simple cases, we can gain insights into the more complex ones.
Exactly.
I can see how this would be relevant in computer science,
Yeah.
especially when designing algorithms that rely on tree structures.
Absolutely.
Yeah.
The efficiency of many algorithms depends on the specific shape and arrangement of the tree they operate on.
Right.
A000065, by quantifying the number of possible tree structures, gives us a glimpse into the potential variations and complexities that algorithms might have to handle.
It's amazing how this seemingly simple sequence keeps revealing connections to such diverse fields.
It is.
We've gone from geometry to graphs to supply chains, and now rooted trees, all linked by A000065.
Yeah.
Is there an end to the reach of this sequence?
The beauty of mathematics is that the exploration never truly ends.
Right.
There's always another layer to uncover, another connection to discover. And speaking of uncovering, there's another fascinating facet of A000065 that I think you'll find intriguing.
Interesting.
It involves revisiting partitions, but looking at them through a slightly different lens.
Okay. I'm ready for another perspective on partitions.
All right.
What's this new angle?
Instead of just looking at the individual parts of a partition, we're going to consider the sum of those parts in relation to the number of parts itself.
Okay.
Interestingly, A000065 also represents the number of partitions where the sum of the parts plus the number of parts is less than or equal to n.
So it's like we're adding an extra constraint based on both the total value and the way we've divided it.
Exactly. It's a subtle shift in perspective, but it leads us right back to A000065, demonstrating yet again how deeply embedded this sequence is within the fabric of number theory.
It really feels like we're uncovering a hidden thread that connects all these diverse areas of mathematics.
Yeah.
It makes me wonder, what other secrets does A000065 hold?
There are always more insights to be gleaned, but I think it's time we turn our attention to one final connection.
Okay.
One that brings us back to the world of graphs and tree width.
Right.
Remember our discussion about graphs with the tree width of n2?
Yes.
Well, there's a hidden structural property linked to those graphs that's directly connected to A000065.
I'm all ears.
Okay.
What is this hidden property?
To understand it, we need to talk about the complement of a graph.
Okay.
Imagine taking a graph and flipping all its connections.
No.
If two vertices were connected in the original graph, they're no longer connected in the complement, and vice versa.
Right.
It turns out that the complements of graphs with a tree width of n2 have a very specific and elegant structure.
Interesting.
But I think that's a conversation best left for our final segment.
Okay. I'm already intrigued. Listeners, stay tuned as we wrap up our deep dive into A000065 and unveil the final piece of this mathematical puzzle. We've journeyed through the world of A000065, exploring its connections to geometry, graph theory, supply chains, and even rooted trees.
It's quite a journey.
You've left me hanging with this intriguing mention of a hidden structural property in the complements of certain graph. I'm ready to unveil that final piece of the puzzle.
Right. Let's rewind to our discussion about graphs with a tree width of n2.
Okay.
Remember, these graphs are almost tree-like,
Right.
but with a touch more complexity. Now when we look at their complements,
Yeah.
those graphs where the connections are flipped,
Okay.
a beautiful pattern emerges.
You mentioned that these complements have a specific structure. Can you elaborate on that?
Absolutely. The complements of graphs with a tree width of n2 cannot contain certain common graph structures.
Oh.
For example, they can't have paths of length 3,
Paths of length 3.
often denoted as P3.
Okay.
Imagine 3 dots connected in a line. That's
Yeah.
a P3.
I see.
They also can't contain complete graphs on 3 vertices,
Yeah.
denoted as K3.
Right.
Think of a triangle where all 3 points are connected to each other.
Okay, so these complements can't have those specific structures. What can they have? What does this restriction tell us about their overall shape?
This is where it gets elegant. When you exclude those structures,
Yeah.
the only way to build the complement is by using components that are all star graphs.
I remember we talked about star graphs earlier. Those are the ones that have a central node and all the other nodes are connected directly to it, forming a starburst pattern.
Exactly. So what A000065 is also counting in a roundabout way is the number of graphs whose complements can be broken down into these simple star-shaped components.
Interesting.
It's a subtle connection, but it reveals a fascinating interplay between the structure of a graph, its complement, and this underlying sequence.
So we've gone from counting the ways to partition a number, to understanding the shapes of simplices, the complexity of supply chains, the arrangement of rooted trees, and now the very specific structure of certain graphs and their complements.
We have.
It's amazing how a seemingly simple sequence like A000065 can have such far-reaching implications.
It speaks to the interconnected nature of mathematics. What might seem like an isolated concept in one area can turn out to be a key to understanding something completely different in another.
This deep dive has certainly opened my eyes to the hidden connections that exist within the world of mathematics.
And for our listeners, we encourage you to embrace that same spirit of exploration. Keep looking for patterns, keep asking questions, and who knows what mathematical treasures you might uncover.
That's a perfect note to end on. Thanks for joining us on this deep dive into the fascinating world of A000065. Until next time, keep exploring the OEIS and all the wonders it holds.